Simply stated, under certain conditions, magnetism can be used to generate electricity. You've seen how generators do this relying on electromagnetic induction. Now let's consider the opposite process, how electricity produces magnetism. You know this effect as electromagnetism. The operation of electric motors is based on this process.
While you saw that an electric generator is used to convert mechanical energy into electrical energy, electric motors do just the opposite. A motor converts electrical energy into mechanical energy. There are basically two types of electric motors. One type operates on DC. This type of motor is similar to the starter in your car, which converts the electrical energy in your car's battery into the mechanical motion of starting your car engine. Small, low-torque DC motors are found in audio tape decks. An AC motor, on the other hand, is constructed to operate on alternating current. This type of motor is most commonly used in household appliances, such as air conditioners, as well as in many industrial applications to run machinery.
Now let's see how motors work. Remember, an electric motor's job is to change electrical energy into mechanical energy. Let's take a closer look.
When a current-carrying conductor is introduced into a magnetic field, the lines of flux are distorted. This is because, as you've already learned, the conductor brings a new set of flux lines with it. The conductor's flux lines circle it in a specific way depending on the direction of current flow. Remember, the left-hand rule for conductors can be used to determine the direction of the flux lines. This rule will help you to visualize the direction of flux lines around the conductor.
The key to the operation of an electric motor is found in the interaction of the two magnetic fields, the stationary field and the moving coil.
You'll remember that magnetic lines of force without any interference will follow the shortest path from the north to the south pole. However, the introduction of circular flux lines from the conductor prevents the magnetic flux lines from pursuing a straight path. This is because flux lines do not intersect.
Instead, a complicated relationship develops between the two sets of flux lines.
Because the conductor's flux lines are circular, they interact with the magnetic flux lines in opposite directions on either side of the conductor. On one side, with both sets of flux lines traveling in the same direction, they become tightly spaced and work together to create a stronger magnetic field. On the opposite side, where the two sets of flux lines run in opposing directions, they become more widely spaced and form a weaker magnetic field. The result of this difference in flux line interaction causes the conductor to be pushed by the strengthened field toward the weakened field. The magnetic push continues until the conductor leaves the field of strong flux interaction.
Magnetic push from stronger field to weaker field is used to create movement in an electric motor. Let's see how the motor is designed to convert magnetic push into a rotary motion.
An electric motor is designed to take advantage of magnetic push. The conductor inside the motor is bent into the shape of a U. It's connected to a pivoting base that allows the conductor to spin between the two magnets. This conductor is called an armature. Around the base of the armature is a split copper ring called a commutator. Outside the commutator are two brushes that slide along the commutator and provide an electrical connection for current to the armature. As the armature is supplied with current, its circular flux lines interact with the magnetic field's flux lines, as you saw earlier. The armature is designed so that the magnetic push, or torque, which results from the interaction between the two fields, causes the armature to rotate between the two opposite poles of the magnets. Because the armature is U-shaped, its flux lines change direction relative to the magnetic field flux lines on opposite sides of the armature.
To see this more clearly, let's look at a graphic representation of a side view of the armature.
The two circles represent the left and right sides of the armature. On the left, current is flowing toward you, represented by a dot in the circle. On the right, current is flowing away from you, represented by a plus inside the circle. You can think of it as the tail of an arrow as it moves away from you. Because current flows toward you on the left side, the flux lines rotate in a clockwise direction. But since current flows away from you on the right side, the flux lines rotate in a counterclockwise direction.
The alternating direction of current flow in the U-shaped armature allows the motor to put magnetic flux line interaction to work. Here's how.
On the left, the armature flux lines distort the field flux lines, and magnetic push moves the armature downward. At the same time, the armature flux lines on the right also distort the field. Here, because current is flowing in the opposite direction relative to the permanent field, flux line interaction causes the armature to be pushed upward. The U shape of the armature creates two opposite flux line interactions that combine to push or rotate the armature within the permanent field. As the armature rotates, it becomes perpendicular to the magnetic field and enters the neutral plane where the interaction of the magnetic field is balanced. Here, there is no longer any push on the armature. At this point, the brushes cut current to the armature. However, because of the rotating motion, momentum carries the armature into the opposite field. Once there, the brushes reestablish contact with the commutator, supplying current and thus ensuring the continuous spin of the armature.
Stop the program and complete activity number 4. When finished, continue watching the program.